So let me at that point to ask Manuel, are you ready?
Yes.
Thank you very much. So our next speaker, Dr. sorry, Manuel Meierhofer from Regensburg University, Dr. Rupert Huber Group, will present us on high harmonic generation. Oops, what is that? Okay, good. So please.
Yeah, thanks a lot for your introduction. Hello, everybody, and welcome to my talk. Before I start, let me thank the organizers for inviting me and also for giving me the opportunity to present our latest work here at this conference. Good, let's start with a quick overview of high harmonic generation. So the investigation of harmonic generation started in gases, where the physics is well described by the three-step model of tunneling, ionization, acceleration, and recollision, just as we heard in the first talk. In this process, photons up to the kilo-electron-volt range can be generated, like this is shown here. Yeah, and then in recent years, people realized that the concept of high harmonic generation can be transferred to a solid state system where the physics is much richer due to the electrons being confined to the periodic potential of the underlying solid. The first results in this direction were obtained in the Kono group, where they showed high harmonic generation from zinc selenide. Then around, I think, 9 years later, the Rees group showed that it's even possible to get non-perturbative harmonic generation going on in zinc oxide with harmonics spanning far over the band gap of zinc oxide. And then later, our group showed the first CEP stable harmonics from gallium selenide, and also we investigated the subcycle dynamics in this process. So from harmonic generation, the idea of light wave electronics emerged. And in there, you use the carrier wave of light as an AC bias to accelerate the electrons within a solid so rapidly that they don't have time to scatter. And therefore, solid state based harmonic generation evolved into a really explosive field where now also first applications emerge. For example, Valleytronics, where you use the intense electric field of a multi-terahertz pulse to transfer photo-generated excitons from the K to the K prime valley, or you use the emitted harmonics from a monolayer of tungsten diselenide to reconstruct the band structure of this tungsten diselenide monolayer. The important point here, I would say, is that you do these experiments with low frequency drivers. So the associated photon energy should be smaller than the band gap of the underlying materials, because otherwise you will get really strong quantum absorption, and therefore you will just dissipate a lot of heat in your samples. Therefore, I would say the ideal test range to do light wave electronics is in the terahertz or in the mid-infrared spectral range, where the photon energy is only on the order of a few milli-electron volts. In this topologically trivial matter, which was used in the experiments which I showed you before, it's still not so easy to do this light wave electronics. And this is because even though the light waves you're using are strong and they oscillate very rapidly, the electrons inside the solid or those solids are not very fast, because they have a finite effective mass inside these materials, and therefore they are inertial. So when you try to accelerate them and they get too much excess energy, they really scatter easily, and therefore the typically achievable real space electron deflection is limited to 1 or maximally 2 nanometers. There is a solution actually, which is topological insulators, or which could be a solution to this problem. Topological insulators are semiconducting in the bulk, but they have a 1 nanometer thin surface layer where they are topologically protected conductors. The dispersion relation of those topological surface states follows a Dirac dispersion with corresponding relativistic velocities. And also in these surface states, there is so-called spin momentum locking, which means that when an electron, for example, travels in the kx direction, it has its spin aligned at a certain direction. And therefore, it cannot simply scatter in the backwards direction, because this would mean that also the spin needs to be flipped. And this effect suppresses backscattering and therefore dissipation in the system. So because of the dispersion and this spin momentum locking, we should see inertia-free motion over very large distances without scattering in those materials. And actually, to test this conjecture, we already performed ultrafast angle-resolved photoemission spectroscopy experiments back in 2018 in a very close collaboration with the Ulrich Höfer group in Marburg. And for this, we employed femtosecond UV pulses to photoemit electrons from the surface of the topological insulator, bismuth telluride in this case. And by analyzing the kinetic energy and also the emission angle of the photoelectrons, one can reconstruct the Dirac-like dispersion relation of this topologically protected surface state, which is shown here and which is filled up to the Fermi level with electrons. And now the question is, when you simultaneously apply a terahertz pulse, so a strong electric field, to your sample, you should accelerate the electrons within the band, and you should see this acceleration in the band structure. And actually, this is what we saw, and this is the first ever subcycle ARPIS movie. And I will show this movie now. So as long as there is no field, nothing happens to the electron population. But when the field ramps up to about 2 kilovolts per centimeter, you see that there is an imbalance in the electrons traveling in one or in the other direction. So from this imbalance, you can extract the current which is flowing in the surface state, and you see that the current, which is here depicted in red, distinctly trails the driving electric field, which is here given in black. And this behavior can be rigorously understood in terms of ballistic motion of the electrons in the surface state. So essentially, as long as the field has one polarity, the electrons will just get accelerated in this direction. And one needs to actually reverse the field to actively then slow down the electrons, because in the surface state, there is simply no scattering mechanism which would decelerate the electrons. And therefore, the excursion of the electrons does not follow the electric field, but rather the vector potential, which is the time integral of the electric field. And because of this quasi-relativistic group velocity, and this is really, really high here, the electrons cover a giant mean free path of around 0.5 micrometers within 1/2 cycle of this terahertz driving field without any scattering. So when you accelerate the electrons in this surface state of the topological insulator, the slope of the band structure, which is proportional to the group velocity of the electrons, suddenly flips sign at the Dirac point. And according to Maxwell's equations, such a dramatic acceleration of charged particles should result in broadband electromagnetic radiation. So the question naturally arises, can we generate high order harmonics from the topological surface state? And recently there was a lot of theory work going on which predicted that there should be efficient mechanisms to produce high harmonics from this surface state. And also there was already a lot of experimental work going on which showed high harmonics from Dirac materials. But the problem, however, always was, was that it's quite hard to separate the contributions from the surface state and the contributions from the bulk on this high harmonic signal. And in the following, I want to show you a reliable strategy to achieve this, namely by tuning the driver frequency of the terahertz pulses or the mid-infrared pulses. So our experimental setup is following. We do high harmonic generation and reflection geometry, and the terahertz electric field is aligned along the gamma k direction of the bismuth telluride sample. And then we detect the emitted high order harmonics. When we start with a high driving frequency of about 42 terahertz, we see nice odd orders here emerging, especially when you consider here that the driving field is rather low with around 7 megavolts per centimeter only. So when we then lower the driving frequency and go, for example, to 37 terahertz, still we only see odd orders, and the same is qualitatively true for 33 terahertz. But suddenly we see something really interesting coming up when you go considerably below 30 terahertz, for example here, 28 terahertz. We see that first that the intensity of the harmonic spectrum is dropping by approximately 1 order of magnitude, but more importantly, we see the emergence of even and odd order harmonics in the spectrum. And I want to show you that the even and odd orders are the fingerprints of surface-based high harmonic generation. And whereas for high driving frequencies, we only see high harmonic generation from the bulk. And the question is, how do I know that it all depends on this driver frequency? So this critical dependence on the driving frequency can be understood from a simple transmission measurement. So you send a terahertz pulse through your sample and look at the transmitted amplitude. And you see for low driving frequencies, there is not a lot of absorption going on, but around 37 terahertz, there is a significant drop in the transmission. And this significant drop corresponds actually to the bulk bandgap of bismuth telluride. So when you use radiation to drive these electrons above 37 terahertz, you excite electrons from the bulk valence to the bulk conduction band, and then those photoexcited electron hole pairs are accelerated into anharmonic motion, and therefore give rise to high harmonics. Because the bulk is inversion symmetric, you will only expect even or odd order harmonics, and this is actually what we see in the experiment. When you drive the system below 37 terahertz, so below the bulk bandgap, the photon energy is not sufficient to drive a 1 photon interband absorption into the bulk, and also the relatively low terahertz field strength are not sufficient for multi-photon interband excitation. And therefore the bulk cannot contribute much to high harmonics. Therefore the high harmonic spectra need to be dominated by the surface. And on the surface, there is no inversion symmetry anymore, so the inversion symmetry is broken, and this should result in even and odd orders, which we also see in the experiment. There is also another hint that there is a different mechanism behind this high harmonic generation, namely when you look at the scaling behavior of the different harmonics. So when you drive the system above the bulk bandgap, so you drive high order harmonics in the bulk, you see, for example, for the 7th harmonic here, at the beginning, it scales perturbatively with e to the 2n, which is in this case e to the power of 14. And then for higher field strength, it starts to saturate off. And when you look in comparison to the scaling behavior of harmonic 14, for example, which is driven by 28 terahertz, so below the bulk bandgap, the scaling law is completely away from what you would expect, which is e to the power of 28. So with those two findings, we can be pretty sure that you can use the driving frequency to select between surface-based high harmonic generation and bulk-based high harmonic generation. And what is going on in the surface is really a curious thing, and actually we have not seen such a behavior before. Let me show you what I mean. So the wave function of the driving field is becoming a really sensitive factor. And in the experiment, we keep the driving frequency, the pulse energy, and the intensity envelope constant. And the only thing we're changing is the carrier envelope phase, so the phase between the carrier wave and the intensity envelope. For example, when you look at a field with a CEP, so a carrier envelope phase of 0, you get a high harmonic spectrum, and then you change the, the carrier envelope phase to 0.5 pi. And then you see that there is a dramatic change in the high harmonic spectra. And here, actually, the minima and maxima just switch places. Or what else could you do? Yeah, you can just go to pi, for example, and then you see that you are back at where you started with 0 pi. And this effect was, as I said, really much to our surprise. So we did a systematic study of this, and we varied the carrier envelope phase in continuously from minus 0.5 pi to 2.5 pi. And you see that you can continuously shift all the harmonics just by changing the carrier envelope phase, which means, for example, that you can measure a 13th harmonic, change your CEP by 3 pi or so, and shift your harmonic up to the 16th order, roughly. Or you can just choose a really odd CEP and generate high harmonic spectra, which are not anymore integer multiples of the driving field, but non-integer multiples. And this finding actually was never made in a conventional topologically trivial solid so far. And we don't see this behavior in the bulk of bismuth telluride either. So when we do the same study, we measure high harmonic spectra for different CEPs, and we also do the systematic scan. We virtually see any CEP dependence. And to understand this, we did full quantum calculation based on the semiconductor Bloch equations, and also the simulations show that the shift should only be present in the surface state and not in the bulk state. So the really interesting thing here is that you can shift all the orders continuously with the CEP, and when you track the intensity of one of the harmonics with respect to the CEP, you see that there is a monotonic rise of the high harmonic intensity and virtually no CEP independent background. And this was never really seen in a conventional dielectric. Therefore, we see a qualitatively different high harmonic generation mechanism compared to the conventional solids. The microscopic origin of this extremely critical CEP dependence can be understood semi-classically, and this is just because the electrons in the surface state simply don't scatter. They follow Bloch's acceleration theorem, which means that the momentum of the electrons follows the time integral of the pulse's electric field, which is shown here. And whenever the vector potential crosses through 0, the electrons travel through the Dirac point. And when this happens, the slope of the band structure, which is proportional to the group velocity, suddenly flips sign, and therefore you would expect this high harmonic radiation emission at this point, or at these points. Yes, so in real space, this means that you have a really dramatic acceleration of the Dirac fermions, which is here calculated via a Boltzmann equation simulation. And as I said, this should then result in really broadband emission of high harmonics. And what makes this mechanism of high harmonic generation so special here is that the nonlinearity happens right in the center of the Brion zone, so at the gamma point of the Brion zone. Whereas in conventional dielectrics, you need to drive the electrons far out in the Brion zone to feel the nonlinearities of the band structure. And therefore, in this topological surface states, you don't need to deflect the electrons really strongly. And therefore, also the weak half cycles at the beginning or at the end of the pulse contribute to the high harmonic emission. And this in the end means that the wave function, the waveform is so important. Then there is another very peculiar feature in harmonic generation in topological surface states, because due to the spin momentum locking, the wave function of the electrons in the surface state have a so-called non-trivial Berry curvature, which is plotted here in color code. This means that when you accelerate the electrons through the gamma point, the Berry curvature drastically changes whenever you go through the Dirac point. And the Berry curvature to lowest order behaves like a magnetic field in real space, and therefore it forces the electrons onto curved trajectories in real space. So in other words, the Berry curvature adds a perpendicular velocity component, which is plotted here in red. This non-classical velocity component, as you see here, always crosses through zero with the same slope. And therefore, when you Fourier transform this red curve, you would find that it only contributes to the even order harmonics. And now to illustrate how the real space trajectory looks like, I also brought you a simulation. And the question is, can we see the fingerprints of the Berry curvature, which forces the electrons onto these curved trajectories in the high harmonic spectra? And actually, yes, you can see the fingerprints when you analyze the polarization state of the various harmonic orders. What we do here is we used a fixed polarizer and a rotatable quarter wave plate, and we extract the so-called Stokes parameter for every harmonic order, which is the orientation angle, the ellipticity angle, and also the degree of polarization. And what you find is that for all odd orders, the harmonic orders are really much aligned to the driving field, which is along here 0 degrees for the orientation angle, while all even orders are rotated away from the 0 degrees by as much as 20 degrees or so. The ellipticity of those harmonics is still rather small, so they're all quite good linearly polarized. And the degree of polarization, interestingly, drops with higher harmonic orders. And also our full quantum mechanical simulations reproduce this oscillating behavior in the orientation angle semi-qualitatively, I would say. So the amazing fact here is that by accelerating the Dirac fermions within only a few half cycles of the driving field allows you to trace back even those non-trivial quantum mechanical details of the wave function, such as the Berry curvature, as I showed you. And we believe that it would be pretty hard to measure stuff like this in conventional transport experiments, even at low temperatures. So let me conclude. I showed you how you can discern harmonic generation from the bulk and from the topological surface state by changing the driving frequency. I showed you that when you drive below the bulk bandgap, you see even and odd orders. And for those orders, we find an unprecedented CEP dependence, which is caused by the Dirac dispersion and the spin momentum locking, which in the end leads to this non-integer high harmonic generation. Additionally, I showed you that it's possible to investigate those subtle quantum mechanical features like the Berry curvature by measuring the polarization of the emitted harmonics. And as an outlook, we believe that experiments like this are a platform to explore topology and relativistic strong field quantum physics in a lab. And probably the Berry curvature is only the tip of the iceberg. Maybe in future experiments, one could even measure stuff like Zitterbewegung or axion dynamics in those systems in the lab. Yeah, in the end, let me thank all the people who were involved in the study. So the experimental teams in Regensburg as well as in Marburg, the theory team here in Regensburg, as well as the team in Novosibirsk who provided the samples for us. And also we acknowledge, of course, funding. Yeah, in the end, also, I want to thank all of you for your attention, and I'm really looking forward to your questions.
Yes, thank you very much, Manuel. Please, questions Yes, Koichiro, please.
Thank you very much for a nice talk. And could you going back to the semi-classical picture on Berry curvature things?
Yes.
Dirac.
Like here. Oh, it's still loading. Let's see here.
Yes. So I'm going back to the Dirac band structure and wave packet motion. Sorry. Yeah.
Here?
Yes. This one.
Oh,
so
yeah.
In this case, no. This
Sorry.
one. Thank you. And this one, you only consider the upside, kind of. Is there any going through the down? Why you only consider the only upside?
Actually, you cannot go down, I think, because the states down here are just populated. So the Dirac cone is populated. The Fermi energy is somewhere here. Maybe we can look at the ARPA spectra once again, because I think from them it's much more clearer. So the electrons are filled up to the Fermi energy up here. So the Dirac cone is like this, and the Dirac point is here, basically. Yeah. So the states down here are just filled, so you cannot move the electrons down there, but they will just go in this direction. And also, I mean, you see it in this experiment, then later, let me just play the movie again. So you see it in the ARPA spectra that you do not push the electrons down here, but they will just go the other branch upwards.
So occupation prohibits the motion to the downside.
Yes, I would say occupation prohibits this.
Okay, I understand. May I make one more question? Or
sure.
Please.
Yes, and please show us non-integer spectrum using 25 terahertz.
Like this.
Yeah. So my question is simple, and you used the only 2 or 3 cycle, very short cycle, short pulse width terrace wave.
Yeah.
And if you increase the pulse width more,
yeah.
What do you expect? Similar thing you can observe, or such a 2 or 3 cycles is necessary to observe this?
So actually, I would say even for longer pulses, you should see this behavior, just because, so from the ARPAS data, we know that the scattering times in the surface state are well below 1 picosecond. And this pulse here is, for example, 100 femtoseconds. So I think you can go maybe to 500 femtoseconds and still see the CEP dependence, because the electrons are just coherently accelerated.
So maybe point is the Dirac electron and the no scattering feature of, okay.
Yes, exactly.
Thank you very much.
Thanks.
Thank you, Koichiro. Please, Vladislav.
Yeah, fantastic results. Thank you very much. I would like to better understand this shift of harmonics when you change the CEP. So I understood that you reproduced the shift with a very simple semi-classical model, but nevertheless, the way I look at high harmonics is that this is a kind of a frequency comb. And to shift the frequency comb, you need a phase shift from pulse to pulse in the time domain. I just don't see how this phase shift appears when you change the CEP. So can you kind of dig a little bit deeper into the physics here?
Yes. So first, the theory was semiconductor Bloch equation, so not just simple semi-classical analysis. And I think what is important here is that whenever you cross or whenever you move the electrons through the Dirac point, you get these emission events. And the timing of these emission events is really important. And therefore you see the CEP dependence. And the timing over the pulse could change, for example, if there is some chirp on the pulse. And therefore you can see maybe that changing the CEP changes the timing and therefore the interference condition in the end on your detector. And this could lead, or this leads to this CEP dependence.
Right, but I would argue that exactly the same physics happens in usual solid-state high-harmonic generation, which is obviously not your short experimental result. That everything is very different from bulk harmonics. But we know that in many measurements where the electron-hole collision does not dominate high-harmonic generation, you can think about the physics here there as the electron wave packet moving. And okay, there's no Dirac point. Maybe this is the reason why I don't see the CP shift in bulk.
Yeah, and also in the bulk, you have no coherent acceleration, but just, yeah, scattering events all the time. So probably the coherent acceleration only happens within 1/2 cycle or so, not over the whole driving field.
Okay.
But good question, yes.
May I ask one more brief question?
Sure, please. Take your time.
Right, so,
we can discuss that more deeply. You have time for questions, please.
Right, so you have two mechanisms of high-harmonic generation here, from bulk and from surface, and you showed that for high terahertz frequencies, the bulk effects dominate. For low terahertz frequencies, you get surface emission, which means that there must be, well, there are terahertz frequencies where you have comparable contributions from bulk and solid. And in this case, I would expect some interesting interferences to emerge. So you have two different mechanisms that generate harmonics in the same frequency, which means that there should be some interesting dependencies that are explained as the interference of these mechanisms. So actually, did you see anything like that?
Yeah, I think this was not the main point of our analysis, but what you can see is when you go lower in driving frequency, that slowly the even orders emerge. It's hard to see here, but here the peaks are more narrow band than down here. So you see slowly that because also the pulses are very broadband, that you start to generate also harmonics from the surface, and then you get like this superposition kind of. But I'm not so sure if you would expect interferences, because so this is just a guess. I mean, in the bulk, you still do not drive coherently. But okay, yeah, so what I can say is we see that the emergence of those even orders is not like step-like, but smooth.
Thank you. Can you elaborate a little bit on the source, on the pump source?
Our pump source, yes, I have a backup slide for this. So this is just a quick overview. So we have a titanium sapphire amplifier, which is working at 3 kilohertz, and we send roughly 4 millijoules to a dual optical parametric amplifier. Both of those arms are seeded by the same white light, so the generated near-infrared pulses are phase correlated. And then you overlap both of the pulses in space and also in time with a delay stage, and then we send it onto a gallium selenide crystal and generate the multi-terahertz driving frequencies or driving pulses.
Okay.
And because they are phase correlated, the CEP of the generated driving pulses is stable.
And the pulse width?
The pulse width is roughly 100 femtoseconds or so.
Okay. Okay, so we have a time for one question, please. Because we joined this session right now on high harmonic generation, and we'll go to our Tuesday agenda to our session with strain effect. So I like to start exactly what time is it, because strain folks will come. I'm sorry, it's 10:30. So we have 5 minutes more to talk. Okay. Okay.
Maybe I could asks another question. Well, I suspect that the answer to a question might be one of your last slides. I was just thinking that if you observe the effects of the Bayer curvature, that this could probably be also a way to distinguish between surface high harmonic generation and bulk high harmonic generation. And then as I thought about it, you already changed the slides, so I don't know if you actually did that. So can you distinguish between these two mechanisms just by observing effects related to Bayer curvature?
That's a good question. So you're referring to, so your question is if we analyze the polarization of the harmonics which are generated in the bulk, right?
Well, yeah. You can also reframe it like this. So I was thinking about, like, again, a situation where you have both contributions, how can you distinguish between them?
I think we did not do this experiment, unfortunately, which would be, of course, interesting. But I think from the bulk, you would not expect a rotation of the polarization because there is no Bayer curvature term, probably. But I'm not so sure.
I think this is exactly the question. That's interesting because in principle, you have Bayer curvature all around the band structure in different places, but not as explicit as in the case of the Dirac points.
No, I think for this question, I have no definite answer.
Okay.
So thank you very much.